Hello everyone. This is my first video. It's been a long time since I've recorded any YouTube video before, but I got really excited today about something and I wanted to share it with you all. And so it's a little thing involving secant of x and a nice substitution for integrals that I think is really nice. So let's start with a familiar integral, secant of x dx. And if you took a Calculus 1 course and you have some sort of teacher teach you how to integrate this, which is most of the time they actually have you remember this, but they teach you how to integrate this, they would show you the following little trick, which is you rewrite the secant of x, but then you write this fraction here. So secant of x plus tangent of x over secant of x plus tangent of x. And you see we haven't changed anything because it's going to reduce to 1. And then you distribute the secant of x to the top. So we get secant squared of x plus secant tangent of x all over secant of x plus tangent of x. And from there, because of that nice little trick, we have a really convenient substitution. So in blue, if I set u equals to secant of x plus tangent of x, then if I take du here, we get the derivative of secant, that's going to be secant of x tangent of x, and the derivative of tangent of x is secant squared of x. And of course there's a dx attached to all that. And well, would you look at that, if you divide this by both sides, you solve for dx. I'm just going to copy this because it's kind of a lot. Yeah, you guys get the point there. You get this big fraction there. Look at that. So if we add all this in, you get the u on the bottom here, and you replace dx with du over secant of x tangent of x plus secant squared of x. And I don't really want to rewrite the whole thing, but you sort of get the point here, which is, actually, I can just copy this up here and put it down here. It's going to be a little bit of a mess, but you guys get the point here, which is these guys cancel out, and we get the very convenient integral from 1 over u du, which gives us natural log of the absolute value of u, but we know what u is up here. It's secant of x tangent of x. Oops, excuse me there. And don't forget the plus c. So now this is great and all, but the problem is, I'm sure if you've been shown this method of solving secant of x or the integral of secant of x in a calculus class before, you might have the very rational thought of, how would you ever think to do something like this? And you'd be right to think that, because it's hard to come up with something like that. That trick of just pulling out a secant of x plus tangent of x over itself is not really generalizable. Now, I'm going to go for another method here, which is going to use sort of a weird substitution that you might not expect. But I feel like, for me, if I were some great mathematician from 300 years ago and I were presented with this integral, this might be the way that I would have first thought to do this and not this other way. So if we start with secant of x here, and maybe most of you thought of doing something like this first if you ever came across this integral, which is you rewrite this as 1 over the cosine of x. Now you might see this and think, okay, maybe we can do some sort of u substitution. What if we do u is equals to cosine of x? But then from there, du is equals to, negative sine of x dx, and that doesn't really do much. So instead, what we can do is I'm going to use a substitution that, again, I'm broken record here, but this substitution is going to come a little out of left field. Just bear with me here. We're going to use t is equals to tangent of x over 2. Tangent of x over 2, where does that come from? You'll see in a second. So t is equals to tangent over 2. So what on earth do we do with that? There's no tangent of x over 2 in, no tangent of x over 2 in this integral. What do we do with that? Well, you'll see soon that this relationship here will actually give us something that we can actually use. And all we need to do is first construct a triangle, a right triangle, with, come on, straight line please. Okay, straight line, with an angle of x over 2. And notice, I'm going to rewrite this here as t over 1. If we look at this in terms of trigonometric ratios, so tangent of x over 2, this angle here. So this is, the tangent is opposite over adjacent. If we think of t as the opposite and 1 as the adjacent, we can think of this here. I'll write the ratios here. We can think of the t as being here and the 1 as being there. And from there, we can actually solve for this hypotenuse of this triangle by using the Pythagorean theorem. And I can trust you guys to do this on your own. It's just the square root of t squared plus 1. Okay, so now we're getting somewhere. And if you think about it, you can actually, and again, I'll label this hypotenuse here. If I take the sine of x over 2, which is going to be opposite over hypotenuse, we're going to get t over the square root of t squared plus 1. And if we take the cosine of x over 2, which we know to be adjacent over hypotenuse, we're going to get instead 1 over square root of t squared plus 1. Okay, now we're getting somewhere. So this sort of out of left field substitution is actually going to help us a little bit, but we're given sine of x over 2 and cosine of x over 2. It's close, but we have a cosine of x. So what can we do with this? Well, let's think about double angle formulas. So I'm going to write down here the two double angle formulas for sine and cosine. So we have sine of 2x is 2 sine of x cosine of x. Now, and I'll write the other one down here just for the sake of it, but you still need to change this a bit in order for it to do anything. So cosine of 2x is cosine squared of x minus sine squared of x. So again, how does this help us? So if we think of, how can I explain this? So pretty much, if you think about the logic of the ratios between the arguments of these functions here. So we have 2x here. I'll write this in a different color. 2x here to the normal x's here. It would be pretty much the same as thinking of x to x over 2. So this statement over here, and I'll move this to the side, is pretty much equivalent to saying sine of x is equals to 2 sine of x over 2. And I didn't give myself much space here. Cosine of x over 2. And if this seems a little confusing, just by looking at it like this, you can think of this as maybe doing a substitution within the equation. So if I say u is equals to 2x, that would make x equals to u over 2. Then maybe what I can instead do is the new equation would be sine of u is equals to 2 sine of u over 2 cosine of u over 2. But the thing is, since u and x can both be any real number that you can choose, it doesn't really matter whether you use u or x, you can just keep it that way. And so this is valid. All right, I hope you guys understood that, and if not, I guess leave a comment and hopefully I can help you understand. But we're going to use some similar logic here for simplifying cosine of 2x. Or not simplifying, just changing it into something that's useful for us. So cosine of x is cosine squared of x over 2 minus sine squared of x over 2. Okay, and now you may have seen where this is going, which is, look, very conveniently, the things that we just solved for, sine of x over 2, cosine over 2, from those triangles from earlier, we have them right here in terms of sine of x and cosine of x. Well, what are we looking for before? We're looking for cosine of x. So since it's not really relevant here, I'll let you guys solve for sine of x if you're curious enough, but right now, we're just going to use cosine of x, since that's what's going to help us most here. So if let me check up here. Right, so sine of x over 2 is t over square root of t squared plus 1, and cosine of x over 2 is 1 over that same denominator. Okay, so that means that we can replace this guy with this guy here, squared. And this one with this one squared. And great, so we still have that here. So again, this is because this is equals to this is equals to this. And so we can just plug that in there, no problem. So let's just simplify that a bit. So 1 squared is just 1, and then the square cancels out the square root. Here we get a t squared. Same root cancellation here. And we can put this all under one fraction. And now with that substitution from earlier, and I'll remind you, the substitution was t is equals to tangent of x over 2. It implies that the cosine of x, normal x, not x over 2, cosine of x is actually equal to this, which doesn't involve any trig functions at all. So this is going to be very useful to us for figuring out this integral. So one last thing before I plug everything back into the integral, because I don't want to get too excited here, just that we need to figure out what dt is. And if I rewrite the integral here, 1 over cosine of x dx, integral of that, still need to solve for dx, or else we can't do anything. So what I'm going to do is I'm going to solve this equation for x. So x over 2 is equals to arctangent of t. That means that x is equals to 2 arctangent of t. And then this is pretty simple. It's just dx is equals to the derivative of arctangent of t. That's just 1 over t squared. And the 2 goes on the top instead. And so perfect. And from there, we can just solve this. So we can plug everything in that we've just found from now. It's really only these two simple little things. So let's do it. The integral of 1 over, and I'll write a big fraction here, 1 minus t squared over 1 plus t squared. And here the dx turns into, I'll write 2 dt on the top here. And I'll write 1 plus t squared here. Now this, see, something convenient happens here. These guys happen to cancel out. So we get the integral of 2 over 1 minus t squared. Now, for those of you who like to watch a lot of math YouTube and all, or just study math on your own, you may recognize this as the derivative of the inverse hyperbolic tangent. But for those of you who might not be familiar with that, I'll go through the steps of figuring this out via partial fractions. But pretty much what I've done here is I've turned this otherwise, I don't want to say difficult because it's not super difficult compared to other integrals out there, but pretty challenging integral into something that's doable. Because all we need to do is just do some partial fractions. So to get started on that, so I'm just going to write this in red down here. So 2 over, and you know this difference of squares is going to turn into 1 plus t, 1 minus t. And we want to split this into two new denominators. A over 1 plus t plus b over 1 minus t. And instead of using the whole cover-up method, I think I'm just going to put up a system of linear equations because that always seems like the safer option for me. So this would imply that 2 is equals to a 1 minus t plus b 1 plus t. And I just did that by multiplying both sides by 1 plus t, 1 minus t. And I should have shown that step, sorry guys. Alright, so distributing these two out, we get a minus at plus b plus bt. And now organizing like terms in terms of t's, we get that 2 is equals to, I'll write the, how would I write this? Alright, let's just put a plus b here. And we have negative at plus bt. Man, I'm having a brain fart right now. At plus bt, and I want to factor out. So I guess that would be a minus t? Let me just make sure that's right. So a minus b, so if you distribute this back in, yeah, it would be the same. Okay, so that's how you would do that. Okay, and I guess you can also distribute this back in. You could have done b minus a. Yeah, that would have been the rational way to do this. But okay, so we have this, and we're going to compare the two sides of this equation by thinking of sort of a 0 times t terms here. So this term here contains a t, this term here contains a t, and I know we just kind of brought it out of thin air, but work with me here. That means that b minus a times t is equals to 0 times t. And obviously, we can always just cancel out the t. So we get that. B minus a is equals to 0. And then these guys both don't have a t. So we can equate them too. And this is a pretty easy equation to solve. It's just, so this top equation, if we add a to both sides, we get that b is equals to a. So if I just replace this b with another a, we'll get that 2a is equals to 2. We get that a is equals to 1, which is also equal to b. So this partial fraction ended up being pretty convenient. So I'll write the integral back in white here again. So we get integral of 1 minus t squared dt. And then we can split that into the integral of 1 over 1 minus t dt plus the integral of 1 plus t dt. Convenient, we can just... So careful with your u substitution on this one, because you can easily mess this up. This is going to end up being minus natural log of t minus 1. You can check that with a u substitution, but be careful. This is not natural log of 1 minus t. And this next one is pretty easy. It's just natural log of that. Don't forget your plus c. And in the end, so Actually, before I wrap this up, so I'm going to write the natural log all in one big thing here. And now remember, we use the substitution t is equals to tangent of x over 2. So that means that, and finally down here, I'm going to write down the secant of x dx is equals to the natural log of the absolute value of tangent of x over 2 plus 1 over tangent of x over 2 minus 1 plus c. So this is great and all until I'm sure you've already realized by this point, wait a second, this is not the same as what we had before, and if I scroll all the way back, which isn't too far, but it's, yeah, look, we get something different. Natural log of secant of x plus tangent of x? Did I do something wrong? Did something happen here? And actually, no, I didn't do anything wrong here, at least I've gone through this method before, I've checked it. And you can check for yourselves that these two expressions, so if I equate these, natural log of secant of x plus tangent of x, to save myself the trouble, I'll just copy this here, are actually equal to each other. And to the curious among you, you might ask, so how can you prove that these are equal? Well, assuming things go well here, I'm probably going to do another video showing that these two are equal. So kind of like a follow-up video. But for now, I would encourage you to take a crack at this yourself because it is a pretty interesting challenge. But for now, thank you so much for watching this video if you did and making it to the end. And well, yeah, I hope you have a great day. Thank you.